In this exercise, we are going to attempt to describe the measurement of the strength of a spring. The details have to be included in the proper hierarchy, and the details we must include are displayed below the figure. So let's talk about the figure. A spring has a certain length, and when there's no force on the spring, it remains at that length. However, when the object at the end of the spring, as in part B, is pushed to the left, the spring pushes to the right. Or in part C, when the object is pulled to the right, then the spring pulls back to the left. Now, the force grows stronger if the object is displaced by a larger displacement. So if we pull, for example, as in part C of the figure, for a large delta x, a large displacement, then the force will be large. But if we barely displace it only by a small amount, then the force back to the left will be small. So the force is proportional to the distance from the equilibrium point, or the unstretched length. The force is always in the opposite direction of the displacement, and we can measure what distance corresponds to which force. In order to do that, we have to provide a known force to understand what force the spring is providing against us. Those should be equal if the object is remaining stationary. We could use a sensor, or we could hang weights from the spring. There are sensors where you can attach them to the gray box, as in the figure, and then pull or push, and the sensor would tell you how many pounds of force or how many newtons of force you are exerting on that object. The spring would then change length, and you could measure the length of the spring and write down that length corresponds to the force measured by the sensor. Or, more simply, you could hang weights from the spring and write down how much mass corresponds to what length of the spring, knowing that mass times the gravitational constant g equals the force provided to the spring. So by hanging more and more weight from the spring will stretch, and you can measure the length versus the weight. These details should be described in a proper hierarchy with any equations properly described, with the variables being defined first. So let's make an attempt. Now, one of these details should come first, and it should be the most general detail. We should probably introduce the equation that describes the spring first and get the variables defined early on in our paragraph. Remember, we want this paragraph to be as short as possible, while still having the proper hierarchy of detail so that the reader understands what we mean. So a good move is probably to describe in words the effect that's being measured in general, and then provide an equation with the proper variables defined. So we could go something like this. The force of a spring is proportional to the distance it is displaced from its unstretched length. What's the appropriate thing to say here? We could say equilibrium length. The force of a spring is proportional to the distance it is displaced from its equilibrium length. The force is always in the opposite direction as the displacement. Let Control B. Let F be the force of the spring, K be the constant of proportionality, between force and displacement, and x be, actually I should put this in bold, x be the displacement. According to Hooke's law, the force is equal to negative kx. So you see that I've defined my equation last. So I've introduced in the first sentence the general idea in words. The force of a spring is proportional to the distance, etc., etc. Then I define my variables carefully in one sentence in a list, and then I introduce the equation. Now, you may or may not know that this is called Hooke's law. You could also just say according to the spring force equation. For example, you could say that. What do we do next? So now that we have the equation introduced, then we will describe how to measure k. That's the goal of the activity. To measure the k value of a given spring, we may hang weights of known masses from the spring while recording the new length as each weight is added. So notice that my writing goes back to being general, but now I've given myself an opportunity to be more concise. So what would I have done had I not defined what is k? Not only would the reader be left to rely just on the figure, or if they didn't have access to the figure, they would just be guessing what I mean. But notice that I can say k value now, instead of just to measure the constant. I'll leave it highlighted or italicized, constant of proportionality between force and displacement. To measure the constant of proportionality between force and displacement. That's 1, 2, 3, 4, 5, 6, 7 words that I can now replace with just one word because I've defined my k value in the equation. So the point is, by introducing the equation, it may seem like additional material, but later on you can continue to reference these variables, and that makes the writing concise. To measure the k value of a given spring, we may hang weights of known masses from the spring while recording the new length as each weight is added. The force applied to the spring given the total mass m hung from it will be m times the gravitational constant g. Each displacement from equilibrium, actually that's not a necessary phrase, each displacement x may be recorded alongside the let's see, do I want to mg so that k will be mg divided by x. This last sentence is a small detail, right? Because if you haven't done this particular experiment before, you may not know that f is equal to mg in this case. But the point is, it's the it's the most meticulous or the finest level of detail, whereas the first sentence here is the general idea. The force of a spring is proportional to the distance it is displaced from its equilibrium length, right? So we go from general to specific, right? How you actually obtain the k value. But notice that we flow from general to specific, and if we need variables along the way, we define them in the equation, but we define the variables first, then the equation. So the hierarchy of this paragraph proceeds like so. The general idea comes first, then any variables, any and all variables comes second. Third comes the equation. Fourth comes the actual procedure, and fifth, if you will, comes the result, or at least the way you would actually calculate k from the data. So I call it the results. So there's a little bit of a tricky part here, because this is obviously the most general. But then if I come down here, variables might seem less general than, or more specific than the equation, but if you think about it, that shouldn't be the case. The variables could be anything. The variable could be any number, right? How specifically they are put together and used must be more specific. So this is less general, but still, any numbers. The equation is specifically how are the numbers used. The procedure obviously gets even more specific. Because it's a step-by-step process, step-by-step description. And then finally, the most specific comes last. So this would be a well-constructed paragraph describing the process for measuring how strong a spring is.